Imagine a universe where the ticking of your clock is an absolute, where measuring a distance depends entirely on how you're moving,
Mm-hmm.
and where gravity isn't some invisible force pulling you down, but like a monumental twist in the very fabric of reality itself.
Sounds like pure science fiction, doesn't it?
It really does. But this isn't fiction. This is the world Albert Einstein unveiled to us, not with, mind-numbing equations, but with surprisingly elegant thought experiments.
And today, we're diving deep into Einstein's groundbreaking work, Relativity, the Special, and the General Theory, published way back in 1916.
Right.
And this wasn't some dense academic tome. Einstein actually wrote it specifically to explain his revolutionary ideas to curious readers, people like you listening, without needing advanced math.
And that's really our mission today, too.
Mhm.
We want to pull out the absolute core insights using Einstein's own words as much as possible. We'll try to clarify the profound concepts of special and general relativity.
Track their astonishing historical confirmations.
Yeah, and explore the huge impact they've had on our entire understanding of the cosmos. So get ready to maybe rethink everything you thought you knew about space-time and gravity. Let's unpack this.
Okay, so we're drawing directly from Einstein's own accessible 1916 book. That means we'll be following his step-by-step logic. He starts with the puzzling challenges facing classical physics at the time, then moves to his, revolutionary solutions, right up to the incredible confirmations like that famous 1919 eclipse that basically rocketed him to global fame.
So to really get Einstein's genius, we first need to step back a bit and understand the cliff edge physics found itself on around the turn of the 20th century. What was that bedrock of classical physics, and where did it start to wobble?
Well, classical physics, built mostly on Isaac Newton's amazing work, gave us this really intuitive, sort of common sense picture of the universe.
Right, it felt solid.
Exactly. We thought of space as this fixed, unmoving stage, like a rigid grid where stuff happened. Time was, universal, an absolute clock ticking away identically for everyone, everywhere.
No matter what.
No matter what. And measurements, like the length of a ruler or the speed of something, they were considered absolute truths. Didn't matter who was measuring or how fast they were moving. It was a comfortable, predictable universe.
It sounds so straightforward, so sensible.
Yeah.
Where did the cracks even begin to show in this seemingly perfect picture?
Well, Einstein started by questioning the very truth of those common sense ideas. He loved using these vivid thought experiments, like his famous railway carriage analogy.
Ah, yes, the train.
Yeah. If you're inside a train moving smoothly, uniformly, and you drop a stone, from your perspective, it just falls straight down.
Seems simple enough.
But now, picture someone standing on the embankment watching that same train whiz by. To them, that stone doesn't fall straight down at all. It follows a parabolic curve.
Right, because the train's moving forward as the stone falls.
Exactly. And this simple observation highlights something really profound. Motion isn't absolute. It's always relative to a body of reference, or what we'd call a coordinate system.
Yeah.
Your perception of reality literally depends on your frame of reference.
Okay, that makes sense. We kind of get that intuitively. Motion is relative. But here's where it gets really weird, because then you bring light into the picture. Classical physics just hit a brick wall with the speed of light, didn't it?
That's where the real intellectual difficulty, the crisis, emerged. For decades, physics had established that light travels at this constant, incredible speed, roughly 300,000 kilometers per second in a vacuum.
The cosmic speed limit.
Right. And crucially, the speed was measured to be the same regardless of the motion of the source emitting it. For instance, the astronomer de Sitter looked at double stars orbiting each other.
Yeah.
So sometimes one star is moving towards us, sometimes away. If light's speed depended on the source's motion, like sound from a moving ambulance, we should see light from the oncoming star arrive faster.
Well, we didn't.
We didn't.
Mm.
Light always arrived at the exact same speed.
Okay, so if you're on a spaceship going really fast, say half the speed of light, and you turn on your headlights, that light still zooms away from you at the full speed of light. That's already weird.
It is counterintuitive. But then classical mechanics, Newton's rules, said if you are moving towards a light beam, you should experience that light beam as moving slower relative to you.
Right, like if you're walking forward on a moving train, your speed relative to the ground is your walking speed plus the train's speed. You'd expect to subtract speeds if you're chasing something.
Exactly. But light just refused to play by those rules.
So this created a huge, apparently impossible conflict.
Yeah.
How could the speed of light be constant and the principle of relativity, the idea that the laws of nature are the same for everyone moving uniformly, how could both possibly be true?
It seemed like one had to give, or there was some really deep misunderstanding of how things worked. Physicists were truly backed into a corner.
And Einstein, with this incredible insight, saw a third way. He didn't just throw out one principle or the other. Instead, he did something much more radical. He completely reimagined reality itself.
He did. He looked again at the very definitions of time and space, things everyone took for granted, and he showed that if you just held on to both the principle of relativity and the constant speed of light rigorously,
What happened?
a new theory emerged logically, almost inevitably, the special theory of relativity. The incompatibility just vanished.
So how did he actually resolve this? It started with rethinking something incredibly basic, simultaneity.
Wow.
What does it mean for two things to happen at the same time?
Yes, exactly. The everyday idea of simultaneous events needed a complete overhaul. Einstein used another classic thought experiment. Imagine two lightning flashes striking distant points, let's call them A and B, on a railway embankment.
Hmm.
Now, an observer standing exactly at the midpoint, M, between A and B, would see those flashes simultaneously. Why? Because the light from both flashes travels the same distance and reaches them at the exact same moment.
Makes sense. But what about someone on a moving train?
Ah, now it gets interesting. Even if that observer on the train passes the midpoint M, at the precise instant the flashes occur, they are moving. Let's say the train is moving towards point B and away from point A.
Okay.
Because they're moving towards B, the light from the flash at B will reach them sooner than the light from flash A, which has to catch up to them.
So they wouldn't see them happen at the same time.
Correct. From the perspective of the observer on the moving train, flash B happened before flash A. This leads to this profound and, frankly, revolutionary realization. Events which are simultaneous for one observer are not simultaneous for another observer in relative motion.
Wow.
As Einstein put it, quite starkly, every reference body, coordinate system, has its own particular time. It blew apart the whole notion of absolute universal time. What's now for you isn't necessarily now for someone moving relative to you.
That is truly mind-bending. The idea that simultaneity itself is relative.
Okay.
What's you?
So if time isn't absolute, I'm guessing distance gets weird too. You guessed right. Just like time, the measured length of an object, say, the railway train itself is not absolute. Its length depends on the observer's state of motion relative to it.
So the person on the train and the person on the embankment would measure the train's length differently.
They would, and neither measurement is more correct than the other. They're both valid within their own frame of reference. Length, like time, is relative.
And these new ideas about relative time and distance, they required a whole new math to describe how measurements change between different moving frames, right? This Lorentz transformation.
Exactly. It replaced the old, simpler Galilean transformation, which just added velocities and assumed absolute time and space. The Lorentz equations showed how space and time actually warp and mix together depending on relative motion.
And the beauty is, this new math naturally keeps the speed of light constant for everyone, no matter how they're moving.
Precisely. It showed that the two assumptions of classical mechanics, that time intervals and space intervals are absolute, were simply incorrect. Drop those assumptions, adopt the Lorentz transformation, and the conflict between relativity and the constant speed of light just dissolves.
This sounds incredibly strange compared to everyday experience.
Yeah.
What are some of the other, really counterintuitive consequences of special relativity that turned out to be real?
Well, there are three big ones that really reshape how we see reality. First, length contraction.
Okay.
A physical object, when it's moving relative to you, actually appears shorter in the direction of its motion than it does when it's at rest relative to you.
Shorter, like physically compressed.
Physically shorter from your perspective, yes. The faster it moves, the shorter it gets along its direction of motion. It's not an optical illusion. It's a real geometric effect of space-time.
That's wild. Okay, so lengths change. And then there's time dilation, which is maybe even weirder.
Yes. Clocks that are in motion relative to you tick more slowly than identical clocks that are at rest relative to you.
Right.
Slower. The faster the motion, the slower the clock ticks from your perspective. This is real, too. Think about GPS satellites. They have to account for this effect. Astronauts on the ISS age just a tiny fraction slower than us on Earth because they're moving so fast.
Wow.
And both length contraction and time dilation point to the same conclusion. The speed of light, c, isn't just fast, it's an absolute, unattainable, limiting velocity. Nothing with mass can ever reach it, let alone exceed it, because its length would shrink to zero and its time would effectively stop.
The ultimate cosmic speed limit. Okay, so it's a beautiful theory, but you need proof, right? Was there experimental evidence?
Oh, absolutely. And interestingly, some evidence existed even before Einstein fully formulated the theory. Remember Fizeau's experiment from the 1850s?
Vaguely. Involved light in moving water.
That's the one. He measured the speed of light in moving water, and it turned out Einstein's relativistic way of adding velocities, not the simple classical way, perfectly matched Fizeau's results from decades earlier.
That's amazing. And what about the really famous one, the Michelson-Morley experiment? That caused headaches for years, didn't it?
A huge headache. In the late 19th century, physicists believed light needed a medium to travel through, this hypothetical luminiferous ether filling all of space.
Like sound needs air.
Exactly. Michelson and Morley designed incredibly sensitive experiments to detect the Earth's motion through the supposed ether, like measuring the ether wind.
Yeah.
But they found nothing. Consistently null results.
Which didn't make sense classically.
Not at all. The physicist Lorentz even had to invent a rather awkward ad hoc contraction hypothesis just to explain away the null result. But special relativity explains effortlessly. There is no ether and there's no absolute rest frame to measure motion against. Length contraction is a natural consequence of relativity itself, not some special fix.
Okay, that clears up a major historical puzzle. And then, of course, the big one, E.V. Malko. What did special relativity tell us about mass and energy?
This is probably the most profound consequence. It's not just a formula, it's a statement about the fundamental nature of reality. Special relativity unified the previously separate laws of conservation of mass and conservation of energy.
How so?
It revealed that mass is a form of energy, and energy has mass. They're interchangeable. Mass isn't just inert stuff, it's an incredibly concentrated form of energy. The soak part, the speed of light squared, is just a huge conversion factor, showing how much energy is locked up in even tiny amounts of mass.
And this underpins nuclear energy, how stars shine.
Everything. It's fundamental. Interestingly, Einstein notes in the 1916 book that direct experimental proof wasn't really available then, but he was confident. Writing it has since been thoroughly proven time and again. Incredible foresight.
Absolutely. And one more piece to tie special relativity together. Minkowski's four-dimensional space. It sounds very sci-fi.
It does, but it's become standard physics. Hermann Minkowski, who is actually one of Einstein's math professors, gave special relativity a powerful mathematical framework. He showed that it's more natural to think of our world not as three dimensions of space, up, down, left, right, forward, back, plus a separate independent dimension of time,
But
as a unified four-dimensional reality called spacetime. An event isn't just located at position, XYZ, it's located at space-time coordinate, XYZT. Space and time are interwoven. What one observer sees as purely spatial distance, another observer in motion might see as a mix of space and time.
So they're not separate stages, they're one combined fabric.
Exactly. Minkowski's formulation really highlighted this deep connection, stripping time of its independent role it had in classical physics.
Okay, so special relativity was a massive leap, dealing with uniform motion. But Einstein wasn't finished, was he? He felt something was still missing. It didn't handle acceleration or, crucially, gravity.
That's right. He found special relativity logically, well, unsatisfactory in a way because it still gave a privileged status to those uniformly moving Galilean reference frames. Why should they be special?
He wanted laws that worked for everyone, no matter how they were moving.
Precisely. He sought a general theory's relativity where the laws of nature would hold true for all observers, whether they were standing still, moving smoothly, or accelerating, spinning, falling, whatever. And this quest, especially focusing on acceleration, led him directly to rethinking gravity.
And this is where we get the famous accelerating chest or elevator thought experiment. It's such a brilliant conceptual leap. What did it reveal?
It's fantastic, isn't it? Imagine you're in a sealed, windowless chest floating way out in empty space, far from any planets or stars.
Okay, total isolation.
Now imagine some external force starts pulling this chest upwards with a constant acceleration. What would you feel inside?
I'd feel pressed against the floor, like gravity was pulling me down. If I dropped something, it would fall to the floor.
Exactly. It would fall with constant acceleration relative to the chest. Now, Einstein's crucial insight was this. That experience, inside the accelerating chest, is completely indistinguishable from being at rest in a uniform gravitational field, like standing on the surface of the Earth.
You couldn't tell the difference locally. Acceleration feels exactly like gravity.
That's the thunderclap moment. This is the equivalence principle, the absolute cornerstone of general relativity. It states that the effects of acceleration are locally equivalent to the effects of gravity.
And this explains something that had always been a bit mysterious in Newtonian physics, right? The equality of inertial mass and gravitational mass.
Precisely. Inertial mass is how much an object resists being accelerated. Gravitational mass is how strongly gravity pulls on an object, like its weight. Empirically, these two masses were always found to be identical, but Newton's theory didn't explain why. The equivalence principle provides the reason. They are fundamentally the same thing, just viewed in different scenarios, one involving acceleration, the other gravity.
Okay, so if acceleration and gravity are two sides of the same coin, what does that tell us about the nature of gravity itself? Does it mean gravity isn't really a force in the way Newton thought?
It fundamentally changes the picture. Think back to the accelerating chest. If you shine a beam of light horizontally across the chest from one wall to the other,
Uh-huh.
from your perspective inside the accelerating chest, that light beam wouldn't appear to travel in a straight line. Because the floor is accelerating upwards to meet the light beam would appear to curve downwards.
Okay, I can visualize that.
Now, apply the equivalence principle. If acceleration is equivalent to gravity, then light must also follow a curved path in a gravitational field.
Whoa, so gravity bends light.
Gravity bends light, which means that in the presence of mass and energy, space itself isn't flat like Euclidean geometry assumes. Light always takes the shortest path. But if space itself is curved, that shortest path isn't a straight line as we usually think of it.
So gravity isn't a force pulling things through space. It's a feature of space-time itself. Mass and energy tell space-time how to curve, and that curvature tells objects how to move.
That's the essence of general relativity. It's a geometric theory of gravity. Mass and energy warp the geometry of space-time around them. Objects and light then follow the straightest possible paths, called geodesics, through this curved space-time. What we perceive as the force of gravity is just motion along these curves.
And this means our standard high school geometry, Euclidean geometry, doesn't perfectly describe reality in the presence of gravity.
It doesn't. Einstein used another thought experiment, a rotating disk. Imagine trying to measure the circumference and diameter of a large, rapidly rotating disk using standard rulers. Due to special relativity's length contraction, rulers placed along the circumference, moving tangentially, would appear slightly shorter than rulers placed along the diameter, moving radially or not at all at the center. So if you measure the circumference and divide it by the diameter, you wouldn't get exactly pi.
Because the geometry on the disk is distorted by the rotation, which acts like a gravitational field.
Exactly. It demonstrates that in the presence of gravity, or acceleration, space can be non-Euclidean. The familiar rules don't necessarily apply.
So if space itself can be curved and warped, how do you even describe locations or map things out mathematically? You can't just use a standard grid.
Right, you need a more flexible system. Einstein adopted Gaussian coordinates, developed by the mathematician Carl Friedrich Gauss, for describing curved surfaces. Think about mapping the curved surface of the Earth onto a flat map. You need projection methods. Gaussian coordinates are a way to label points on any curved space or surface, even if it's changing.
And he had this image of a reference mollusk.
Yeah, it's a great visual. He imagined this infinitely flexible, non-rigid reference body, like an amoeba or mollusk, that could contort and adapt to the curved space-time. It's his way of saying that our coordinate system itself has to be flexible, not fixed, to describe a reality where geometry isn't rigid. Any consistent labeling system, any Gaussian coordinate system, is equally valid for describing the laws of nature.
This is just conceptually staggering. Pure thought leading to this entirely new picture of gravity and spacetime.
Yeah.
But crucially, general relativity wasn't just thought experiments. It made specific testable predictions, didn't it? And they were confirmed.
Absolutely. And the confirmations were stunning, really cementing the theory. There were three major early ones. First, the perihelion precession of Mercury.
Right, Mercury's weird orbit.
Exactly. Astronomers knew for decades that Mercury's elliptical orbit around the sun wasn't perfectly stable. The point of closest approach, the perihelion, slowly rotates over time. Newtonian gravity could explain most of this rotation due to the pulls of other planets, but there was a tiny discrepancy left over, about 43 arcseconds per century.
Just a sliver, but unaccounted for.
A persistent, annoying sliver. General relativity, when applied to Mercury's orbit in the curved space-time around the sun, predicted exactly that missing 43 arcseconds per century. No fudging, no extra parameters, it just came out of the equations.
Wow. That must have been a huge
It
boost.
was massive, a major puzzle solved cleanly. Then came the most famous test, the deflection of starlight by the sun's gravity.
The 1919 eclipse expedition.
The very one. Einstein predicted that light from distant stars passing close to the sun would have its path bent by the sun's gravity, making the stars appear slightly shifted from their usual positions in the sky.
How much of a shift?
A tiny amount, about 1.7 arcseconds for stars seen right near the edge of the sun. You could only observe this during a total solar eclipse when the sun's glare is blocked out.
So, Sir Arthur Eddington?
Led expeditions in 1919 to Sobral, Brazil, and the island of Principe off West Africa. They took photographs of the star field around the eclipsed sun and compared them to photos of the same star field taken at night months earlier. And the results matched Einstein's prediction beautifully. The stars were deflected, and by the amount general relativity predicted, the news exploded worldwide. Einstein became an international superstar overnight. It was dramatic proof that gravity really does bend light and warp space.
Incredible. And the third confirmation, gravitational redshift.
Yes. This follows from the equivalence principle and time dilation. Clocks run slower in stronger gravitational fields. Since atoms emit light at very specific frequencies, and you can think of atomic vibrations as tiny clocks, light emitted from a place with strong gravity, like the surface of a massive star, should have its frequency lowered, shifted towards the red end of the spectrum when observed from a place with weaker gravity, like Earth.
It loses energy escaping the gravity well.
Effectively, yes, the light waves get stretched out. This effect is tiny for the sun, but observable. It was conclusively confirmed a bit later, in 1924, by Walter Adams, who measured the light from the incredibly dense companion star of Sirius B.
A white dwarf.
Exactly. It's super dense, so its surface gravity is immense. Adams found a redshift 30 times greater than the sun's, matching the predictions of general relativity perfectly.
So 3 major distinct predictions all confirmed. That's powerful evidence. Okay, so from special relativity changing space and time to general relativity explaining gravity as space-time curvature, Einstein then turned his attention to the biggest picture of all, the universe as a whole. Cosmology.
He did. And here, too, classical physics, Newtonian mechanics ran into problems. When you tried to apply Newton's gravity to the entire universe, it got awkward.
How so?
Well, if you imagine the universe filled with an infinite amount of matter, distributed roughly uniformly, Newton's law led to infinite gravitational forces, which doesn't make sense.
Okay, so what if it's finite? A finite amount of stars in an infinite space.
That also felt wrong. It implied the universe had a center, and that over time, stars at the edge would just drift off into the infinite void, leading to a gradual impoverishment of the central region. It seemed unstable and, frankly, aesthetically unappealing. Newton's theory didn't offer a satisfying large-scale picture.
So how did Einstein's general relativity offer a different perspective?
It opened up entirely new possibilities because gravity was now linked to geometry. He realized that just like the surface of a sphere is finite in area, but has no edge or boundary.
Right, you can walk forever on a sphere and never fall off.
Exactly. Einstein proposed that perhaps our three-dimensional universe could be analogous to that sphere's two-dimensional surface. If the average density of matter in the universe is greater than 0, which it clearly is, then general relativity allowed for the possibility that space itself could be curved back on itself, creating a universe that is finite in volume, yet unbounded.
Finite, but without edges. Like a 3D version of a sphere's surface.
Precisely. A spherical or elliptical geometry for the cosmos as a whole. In this model, the universe contains a finite amount of matter, but there's no center and no edge to drift off from. The geometry itself is determined by the matter within it.
That's a much more elegant picture. But then came a twist, didn't it? The idea that this finite, curved universe might not be static.
Indeed. Einstein himself initially assumed the universe was static, unchanging on the largest scales. His original equations didn't quite allow for that naturally with matter present, so he actually added an extra term, the infamous cosmological constant, to kind of force a static solution.
His biggest blunder, he supposedly called it later.
Well, maybe, because shortly after, in the 1920s, the Russian mathematician Alexander Friedmann looked at Einstein's original equations without the cosmological constant and showed they naturally predicted something else entirely.
Which was?
An expanding or contracting universe. If the universe wasn't perfectly static, the equations showed space itself must be dynamic, either growing or shrinking over time.
Wow, so the expansion was built into the original theory.
It was a natural solution. And then came the observational proof.
Edwin Hubble.
Edwin Hubble. In the late 1920s, studying distant nebulae, which we now know are other galaxies, Hubble observed their light was consistently redshifted. And crucially, the farther away a galaxy was, the greater its redshift, meaning the faster it was moving away from us.
The Hubble law. Direct evidence that the universe is expanding.
Exactly. It was stunning confirmation that Friedman's interpretation of Einstein's equations was correct, and the universe wasn't static after all. Space itself is stretching.
Though Einstein mentioned the remaining puzzle even then.
Yeah, he notes a little incongruity in an appendix added later. Based on Hubble's early data from the 20s and 30s, the calculated age of the expansion seemed too short, maybe only 1 billion years or so, which conflicted with estimates for the age of stars and the Earth, which were thought to be older.
A reminder that science is always refining things.
Absolutely. Those early measurements weren't perfect, and our understanding of cosmic evolution has grown immensely since then. But it's interesting he pointed out that tension. He also noted that the expanding universe models, unlike his preferred static model, didn't necessarily require space to be finite, though they allowed for it. Its ultimate geometry, finite or infinite, is still something cosmologists investigate today.
So let's try to wrap this up. We've gone from questioning clocks and rulers to bending light and expanding space. What's the takeaway from this deep dive into Einstein's book?
Well, it's hard to overstate the impact. From this one relatively accessible book, Einstein completely overturned centuries of thinking about space, time, and gravity. He showed that our everyday intuition is just limited. It breaks down at high speeds and strong gravity.
And he didn't just tear down the old ideas, he built a new framework that explained existing mysteries, like Mercury's orbit.
Exactly. And made these incredibly bold predictions, like bent starlight, that were then spectacularly confirmed, changing our view of the cosmos forever.
It really is a testament to the power of pure thought, isn't it? Starting from simple principles, the constancy of the speed of light, the equivalence of acceleration and gravity, and following the logic relentlessly to arrive at this revolutionary picture.
And he genuinely wanted people to understand it. That's why he wrote this book, using analogies like trains and elevators, trying to convey the core ideas without getting bogged down in complex math. It wasn't just about immensea, it was about giving us a new way to perceive reality.
What stands out most to you when you reflect on this work?
For me, it's the sheer, almost unbelievable audacity of questioning the absoluteness of time. Everything in classical physics rested on that foundation. To challenge it and then to build a consistent predictive theory upon that challenge, and for that theory to turn out to be right, it's just astounding. It fundamentally altered our place in the universe.
It truly did. And maybe a final thought for our listeners. If matter and energy dictate the geometry of space-time, as Einstein showed, and if that space-time fabric is currently expanding, what does that imply about the ultimate beginning and the ultimate fate of our universe? How much more about this grand cosmic design is still waiting to be uncovered by the next Einstein? The journey, it seems, is far from over.